And go.
Hello everyone, we are Tina and
Hendrik. Today we are talking about green programming. This talk is split into 3 major chapters. We will start with a general introduction into the rising problem of energy consumption. Afterwards, we will define the term green software and move on to green programming.
Then we will present the algorithm we are going to use to create our own experiment and share the results and an evaluation based on our findings. Lastly, we will go over some tools, other environmental aspects, possible steps you can take to move to a greener product, and end with our conclusion. The worldwide energy consumption is on the rise. The main reason for this is economic growth and industrialization, population growth, urbanization, increase of living standards, climate change, and also technological developments and digitalization. With the technological development comes an increase of the number of data centers.
According to Goldman Sachs research, data centers worldwide consume about 1 to 2% of overall power, rising to 3 to 4% by the end of the decade. The workload of data centers nearly tripled between 2015 and 2019. During this time, the data centers' demand for power did not grow because the data centers themselves grew in efficiency. But since 2020, the power consumed by data centers has risen, with AI being one of the main reasons.
The spread of AI and machine learning requires enormous computing power, as these technologies process large amounts of data and perform complex calculations. Training phases of AI models are particularly energy intensive. Goldman Sachs reports that a single ChatGPT query requires about 3 watt-hours of energy, compared to 0.3 watt-hours for a Google search. That's an increase by a factor of 10. They also estimate the overall increase in data center power consumption from AI to be in order of 200 terawatt-hours in the years between 2023 and 2030. By 2028, the analysts expect AI to represent about 19% of data center power demand.
But not just AI drives energy consumption. We will take a closer look at the other driving factors as well, like the increase in data traffic. With the digitalization and growth of the internet, the data traffic has increased massively. We have streaming services, social media, cloud computing, online games, and the general use of the internet, which generates enormous amounts of data that need to be stored, processed, and transmitted. Data centers are the backbone of these activities and require significant amounts of energy to handle the increasing data traffic.
Growth of cloud services. More and more companies and private individuals are using cloud services for data processing and storage. Cloud platforms such as Amazon Web Service, Microsoft Azure, and Google Cloud host millions of applications and websites, driving up the energy consumption of data centers.
Blockchain and cryptocurrencies. The spread of cryptocurrencies such as Bitcoin has greatly increased energy consumption in data centers that carry out so-called mining activities. Mining requires a large number of computing operations, which are carried out in specialized data centers.
Increased availability and redundancy requirements. Companies and organizations are increasingly demanding higher availability and resilience of their IT services. To meet these requirements, many data centers operate redundant systems and storage capacities, which increase energy consumption.
Cooling requirements. Data centers generate considerable amounts of heat from their services and IT equipment. To ensure trouble-free operation, they need to be cooled intensively, which accounts for a significant proportion of total energy and also water consumption.
Exponential growth of network devices. As networking of household appliances, vehicles, machines, and other devices progresses, the amount of data to be managed and processed also increases, requiring the data centers to use more energy. So we see IT and software have a huge impact on the worldwide energy consumption. This means that this topic is something that we should all have in mind when we are creating software, because there are things that we can influence.
Now let us define what green software is. First, this is a huge field. We use the definition of green software from the Green Software Foundation. With green software, we want to focus on reducing carbon emissions. This can be done by focusing on using fewer physical resources. For example, if you create a new software that requires users to upgrade their hardware, this will create more carbon emissions. Long gone are the times where a hardware product was designed for life, or even for a 10-year lifespan. Nowadays, we live in an economy that wants you to update your hardware every year. The production of new hardware alone uses a lot of energy and other resources. We should aim to go back to the longevity of products, even if that means losing out on profits.
Using energy more intelligently. This means consuming lower carbon sources of energy or consuming electricity in a way that helps accelerate the energy transition towards a low carbon future. For example, there are data centers that run on renewable energy. We will go into detail on this topic later. Using less energy. This means that the software you produce uses less energy. This can be influenced by the programming language you choose. With this talk, we want to focus on using less energy by choosing the optimal programming language for your purpose. If you want to find out more about the Green Software Foundation, we have linked the organization here. They are split into 4 different working groups. The Standards Working Group, which focuses on defining baseline specifications for green software. The Policy Working Group, which focuses on where the Foundation's trademark can be used and if it's used correctly. The Open Source Working Group, which focuses on directing the open source, open data, and research community to the field of green software and develop tools to improve monitoring and measuring green software. And the Community Working Group, which focuses on creating partnerships, content, events, and programs. They also have a huge repository of material related to this topic. It includes resources for tooling, organizations, courses, and research material.
There's also the Sustainable Digital Infrastructure Alliance. Their vision is to drive change at the foundation of the digital economy, its physical infrastructure. They focus on achieving a regenerative digital economy by leveraging innovation, collaboration, and policy advocacy. They want to create a digital infrastructure that is not only efficient and resilient, but also in harmony with our planet's ecological boundaries. Check out their website and roadmap for their sustainability goals by 2030. And one last one. If you are a gamer or work in the gaming industry, you might find the Playing for the Planet Alliance interesting. They are supported by the United Nations Environment Programme, UNEP, and sustainability in the gaming industry is their main focus. They help companies in the video game industry to reduce their carbon footprints. Therefore, they offer guidance and tooling like a specialized carbon calculator. An annual event organized by the organization is the Green Game Jam. It challenges game developers to integrate green activities, like, for example, raising awareness about environmental issues into their games. In 2023, famous companies like Rovio, Gameloft, and Tencent participated in their Green Game Jam.
Also at this year's ACCVU conference, there was a talk about this topic called Green Software Architecture. Giovanni Asproni talks more about the environment of where the software runs and how the software is structured. He briefly mentions the programming language issue that we are talking about in this talk here. This is a really good talk if you want to get an overview of many different aspects of green software. As said before, we will focus on the programming language part of the green software topic.
Green programming or green coding is a series of principles applied to software development that aims to reduce the ecological footprint of software. The goal is to write energy-efficient code, use resources economically, and use environment-friendly technologies to reduce the CO2 footprint. This can be influenced, for example, by the programming language you choose. Which brings us to the research paper named Energy Efficiency Across Programming Languages by various authors, which this talk is inspired by.
This paper presents a study of the runtime, memory usage, and energy consumption of 27 well-known software languages. They monitored the performance of these languages using 10 different algorithmic problems programmed in each of those languages. The results show the speed of the programming languages, the energy consumption, and how it is influenced by memory usage. They also show how to use the results to provide support to decide which language to use if energy efficiency is a concern. These are the algorithms they tested and the programming languages they used. The languages are divided into the categories functional, imperative, object-oriented, and scripting.
And here are the results of 2 different algorithms for all the programming languages. The algorithms are Pfannkuchen Redux, which is an algorithm which calculates the maximum number of flips to sort an integer sequence, which is a permutation, and FASTA, which is an algorithm about random DNA sequence generation. As you can see, and unsurprisingly, the tables are led by the languages that are compiled directly to machine code. Although the most energy-efficient language in each benchmark is almost always the fastest one, there is no language consistently better than the others. The paper also analyzes if maybe the memory consumption has an impact on the power consumption, as the fastest language also used the least memory, but found no correlation. It seems like runtime is the biggest factor on energy consumption. We provide a link to this paper in the sources section at the end of the slide deck if you want to check it out for yourself.
Now we will see if we can replicate these results. We also want to analyze for ourselves if we can find best practices for green programming. We looked for an algorithm that is easy to implement in different languages, but complex enough to actually measure something. Additionally, the algorithm should not be standard, so there's no highly optimized library function for that. So we landed on an algorithm that is used to allocate seats in parliaments for proportional representation systems. If you watched my How to Rangeify Your Code talk, you will recognize this one.
So, how does this algorithm work? We will explain it by example. First, we have a certain number of parties competing for seats. Here we have 3, as you can see in the headline of the table. Each party received a certain number of votes. The Hond algorithm will allocate seats to these parties approximately in proportion to the number of votes they received. To do that, we need the numbers of seats that can be allocated. Here we have 7. That's all the input we need. Now we count from 1 to the number of seats. We divide the number of votes by this counter for every party. This gives us a vector of quotients for each party, which we merge into a single vector. Afterwards, we sort the merged vector in descending order. Now we take as many elements from the sorted vector as we have seats to allocate, here 7. Finally, we count the appearances of each party in this sorted subrange. And that's the final result.
To implement this in C++, we used 2 different approaches. One uses standard ranges and the other one uses algorithms. We are going to show the ranges version here. First, we start with the calculation of the quotients for each party, which is highlighted in green on the table. For this, we need to generate all numbers from 1 up to the total number of seats. Then we divide each party's vote count by the seat counter and store the result in a range. To do this, we write a function that has a map of party and votes and total number of seats as their input. To count up to the number of seats, we use an iota view, which starts with 1 and ends with the number of seats plus 1, as the end count is exclusive. Then we calculate the proportional votes, aka dividing the number of votes by the seat counter, using a Cartesian product, which is a view that combines all elements of all views with each other. Or to put it another way, this is a nested loop.
Then we call transform on the Cartesian product view to calculate the divisions. We need to keep the information of the party, therefore we return a struct with the party and the quotient. In the end, we store the results in a vector. Now we need to sort the quotients. To do that, we call standard sort with the function standard greater, as we need to sort in descending order, and we use a projection to tell the sorting function on which member of the struct we want to sort.
Lastly, we need to count the number of seats per party by using the sorted range. We take the first 7 elements of that range, as this is the number of seats that we have, and we count how often the parties appear in that subrange. First, we select the keys from the input map, as they contain the party names. Then we transform the keys and call the count seats per party function. And count seats per party gets the proportional votes and the total number of seats as input. It returns a lambda that is then called by the transform view. In this lambda, we call another function to calculate the actual number of seats. Then we return a pair of party name and seat count. And the calculate number of seats method uses countIf and the take view to count how many seats each party got. As the count seats per party function returns a pair, we can use range 2 to construct a map, and this is what we return from the function. Here's an overview of the algorithm without the helper functions.
We generate all numbers from 1 up to the total number of seats using the iota view. We combine each number with each party and their votes using the Cartesian product. For each party, we divide its votes by all these numbers using the divide by seat divisors function. We use ranges 2 to store the results in a vector. The vector of all quotients from all parties is then sorted in descending order by using standard sort with the function greater and a projection to the member of the struct we want to sort on. From the original votes per party map, we take the party names by using the keys view. We then call the transform view on the party names. They are handed over to the lambda returned by the count seats per party function. In this lambda, we take as many elements from the vector as there are seats to allocate. Then we count how often each party appears in the subrange, which yields the number of seats each party gets. This is in the end written into a map by again using ranges 2, which contains the party name and the number of seats for each party. We implemented this algorithm in 14 different programming languages. Here is a Python version. If you want to review all versions for all programming languages, you can go to our GitHub using the QR code on the bottom right corner of the slide. We uploaded all the code examples and the code to reproduce the results there.
Now we know which algorithm we want to use, we need to talk about the rest of the experimental setup. What programming languages do we want to choose? How do we measure energy consumption of the relevant components like the processor, the RAM, and how the CO2 emissions are calculated? First, we need to decide on the programming languages. One of the many ways of categorizing programming languages is to look at how they execute code. Some languages like C, C++, or Rust are compiled to machine code, which is directly executed by the processor. They also hand over the management of the program's memory to the developer. These things are often believed to create the fastest programs. Other languages, like Java, compile to bytecode, which is executed by a specialized virtual machine. It may figure out hot paths during runtime and optimize the bytecode accordingly. These languages usually manage memory via garbage collection, so the developer does not need to consider this aspect in their code.
Some other languages, like Lisp, can be interpreted line by line. We want to include at least one language of each of these categories. If the execution of the program involves additional components which are run alongside the program, these components will also consume energy. This can be the case for a garbage collector or the VM executing the bytecode or an interpreter. We use the programming languages which you can see here on the slide. It's a good mix of the different categories we just mentioned.
All languages receive the exact same data as input, perform the Hond algorithm, and print the results out to the console. The languages differ in calculation and memory management and how their standard library is implemented. The algorithm relies on sorting, which is taken from the standard library, and printing the results, which is also a standard library function. For C++, we will look into two different implementations, one with ranges and one without. We thought it might be interesting to see if different parts of the standard library yield different results.
Everything is executed on a machine with an Intel Core i7 processor and 8 GB RAM. The computer is a Windows machine, but the code is executed within the WSL. All programming languages receive the exact same input, which is 10 parties competing for 50,000 seats, which is hard-coded into the source code. No file access or network communication is done. The only I/O is printing the results for the 10 parties to the console output after the calculation has finished.
We use the CodeCarbon Python package for tracking and calculating the energy consumption and CO2 emissions. We run all examples for the different programming languages from one central Python script and measure only the execution time. The compile step is not part of the measurements, if there's any. CodeCarbon can track the energy consumption of RAM via an assumption of 3 watts per 8 gigabytes of RAM used. The CPU is measured via the Intel Power Gadget for Windows or the RAPL files for Linux. If you're running a Mac with Apple Silicon chips, the Power Metrics tool is used for tracking.
If none of these is available, CodeCarbon will look up your processor in its database with over 2,000 Intel and AMD CPUs and retrieve its thermal design power, or TDP. It will then assume a constant energy usage, which is 50% of the CPU's TDP, which is an empirically tested value coming from the authors of CodeCarbon. The GPU can also be tracked and measured directly, but only for NVIDIA GPUs. This is done via the PyNVML package. Note that we did not do any programming for the GPU. For estimating the CO2 emissions, the energy consumption of a program is used together with a database of energy production mixes for different countries. Your geolocation is determined automatically for this calculation. Monitors and other periphery consume energy as well, but are not considered by code carbon. We rely on one single Python script, which compiles and executes all languages in one place for convenience reasons. Only the execution time of the algorithm is measured.
This is done by using the emissions tracker context manager, like in the example above. All code in the context manager is measured, and code carbon will automatically figure out how to measure CPU, RAM, and GPU energy consumption. With these values, we can calculate the CO2 emissions based on your current geolocation. After the Python script is finished, code carbon will create a single CSV file with all the measurements. If you have several different measurements, it's a good idea to give them names. This can be done via the project name argument in the emissions tracker. You can also just measure already compiled programs with code carbon. We choose to put also the compilation step in one single script for convenience reasons. It makes rerunning the whole experiments easier if something has changed in the code. There's also an alternative to the emissions tracker called offline emissions tracker. It will not automatically determine your geolocation, which means you have to provide it via the country's ISO code.
This can be useful if you want to see how your carbon emissions would change by moving your application to another country. For the USA and Canada, also states and provinces can be supplied for more fine-grained results. If you're using the Google Cloud or are just generally interested in its carbon emissions, you can also provide the Google Cloud region alternatively, and you will get back greenhouse gas emission data, especially for that Google Cloud region coming from official Google data. Code carbon uses the carbon intensity, emissions per power, which is usually measured in kilograms CO2 per megawatt hour for a country, which is published on the scientific online publication Our World in Data for its calculations. But what does this data consist of?
In order to estimate the carbon intensity for a country, information on the energy resources is needed. Code carbon uses the table shown in the slide for their explanation of their methodology. The emissions data for fossil fuels comes from the US Environmental Protection Agency. The data for renewable energy sources was obtained from the report Comparison of Life Cycle Greenhouse Gas Emissions of Various Electricity Generation Sources from the World Nuclear Association. This is an international organization representing companies from the nuclear industry. You might be wondering why things like solar and wind have a non-zero carbon intensity. That is because the report also takes the non-operational carbon emissions into account that comes from construction. With this table, we can understand how the CO2 emissions of any country can be estimated by using their energy mix.
Let's have a look at the German energy mix for the year 2023. In the bar plot, you can see the energy that was produced in that year in terawatt hours for the different energy sources. Low carbon intensive sources make up about 45% of all energy, resulting in a carbon intensity for Germany overall of 380 kilograms CO2 per megawatt hour. Norway, where we are right now, has a completely different energy mix, which is dominated by hydroelectricity, yielding a much lower carbon intensity of 30 kilograms CO2 per megawatt hour. On the previous slides, we looked at the energy mixes and CO2 emissions for the public power grid. This is the energy mix we use on average.
Some companies publish more detailed information on their CO2 emissions. For example, Google has a dedicated website where you can look up the carbon intensity and the percentage of renewable energy for each of their cloud regions. They also mark low CO2 regions in this table to help you decide where to host your cloud service. They also offer the possibility to automatically select low carbon regions when you create a new cloud resource. Amazon releases a global carbon footprint and information of which of their regions run on 100% renewable energy. But no individual carbon intensity per region is given. Instead, you can access a dashboard with your personal CO2 information in your AWS account. Microsoft offers a dashboard for Power BI, which calculates and visualizes greenhouse gas emissions for your Azure cloud usage.
Now that we have shown you the setup and what we use for measuring energy consumption and CO2 emissions, we are going to look at the results. For visualization purposes, we normalized energy consumption by dividing all measured results by the overall minimum value, yielding one normalized energy unit. All upcoming slides will use this unit. In the table above, you can see its actual value in kilowatt hours and the associated CO2 emissions estimated by Code Carbon for Germany, that's where we are from, the USA, because they host the most data centers, and Norway, for obvious reasons.
The decision of choosing where the code is executed can have a huge impact, as you can see in these numbers. Without changing a line of code, just by moving from Germany to a data center in Norway, the CO2 footprint of your code could be diminished by a factor of 10. Here are the results of the measurements of the Hound algorithm for all programming languages we showed. In this plot, you can see the normalized energy consumption for each program measured by Code Carbon. Just by looking at the bar plot of the results, you see that the compiled languages which use manual memory management uses the least energy, while interpreted Lisp uses the most energy, followed by C# with its running VM and the garbage collector. Looking deeper into the data reveals that the measured energy consumption is almost proportional to the duration of the execution time of the algorithm. Deviations from 100% proportionality come from the energy used by the RAM.
Looking at the exact numbers, we see that C and both C++ variants are very close to each other. In most other experiments of such kind, C is usually the best language, but we also have to take the accuracy of the measurement into account here. Repeating the experiment several times shows that the numbers can vary by plus minus 0.3 after normalization, which means that basically all results within this range cannot be distinguished from one another. If we go beyond individual programming languages, we can find general trends for the categories of programming languages. Compiled languages with manual memory management consume the least energy. There is a large variation within the VM-based languages like Java, Kotlin, Python, and C#. Looking at the numbers, we see that the choice of programming language can influence the energy consumption by a huge factor.
The total energy used is nearly proportional to the runtime of the algorithm, and it's dominated by the CPU. The smaller component is the RAM. C++, C, and Rust have the smallest energy footprint for RAM, while Lisp has the highest one. The deviations here are interesting because all languages receive the exact same data and therefore store the exact same intermediate results. So the difference here can only come from the way the languages stores and manages memory.
What can we learn from these results, and what can you do to improve the energy and CO2 footprint of your software? The results show that different programming languages have a vastly different level of energy consumption and therefore CO2 emissions using the same algorithm and dataset. In our case, this was mainly influenced by the execution time and only a little bit by memory usage. But the results may differ a lot depending on the actual algorithm you want to analyze. We looked at a program with a focus on computations like divisions and sorting without any kind of I/O like network or file communication. We also didn't do any programming for the GPU.
As it was shown in the paper we discussed at the beginning of the talk, the smallest energy footprint achieved was by languages which compile to machine code directly and do manual memory management. In general, it doesn't seem to matter which one of these compiled languages you choose when you want to reduce your CO2 footprint. In the end, it comes down to the purpose and what you're more comfortable with. The efficiency of a program also comes from good optimization. For example, it would not bring you much runtime speed if you would compile C++ without any optimizations. C and C++ also profit from highly optimized compilers, which are worked on for decades now. There are more specialized compilers like the Intel C++ compiler, which utilizes hardware acceleration features for even faster programs.
If you look at these kinds of experiments, you might be tempted to rewrite your software in a language which has a better position in such benchmarks, but this is usually not a good idea, for two reasons. A rewrite takes a long time and consumes a lot of resources. It might take a very, very long time until you are saving more energy than you have invested in your rewrite. And secondly, not every programming language is suitable for every task. You wouldn't do database queries only in C++, for example. Therefore, the choice of language also needs to take the purpose into account.
Instead of a rewrite, you can rely on optimized libraries where the core algorithms are written in a language which are compiled to machine code. For example, in Python, you can use NumPy for array-like operations instead of doing the same in native Python. But keep in mind that while this can help improve runtime, it will never be as fast as using the compiled languages directly. The pros and cons need to be evaluated from case to case. Sometimes also a different implementation of your programming language might be available. You could use, for example, PyPy as a drop-in replacement for CPython. PyPy is usually more performant due to its just-in-time compiler.
Looking at the theoretical runtime complexity of your algorithm and looking for better alternatives is also always a good idea. An example for this can be sorting algorithms, which vary a lot in complexity. Also, not every program needs to be highly optimized. If the program is only used by a handful of people twice a year, who cares about optimization? That will not make a difference. But algorithm-intensive programs that are executed often will highly profit from optimization. We also want to highlight some helpful tools. We develop software for desktop PCs, so energy consumption was never an issue for us before. But if you develop for battery-powered devices like smartphones, energy consumption has always been something to optimize for. Now this is also gaining some traction for other applications. We already discussed Code Carbon as a very useful tool for measuring the energy consumption and CO2 emissions of code due to its versatility, but there are more tools.
There's also the Intel Performance Counter Monitor, or PCM, which provides an API and tools into the energy metrics of a large set of Intel processors. It runs on many operating systems, including Windows, Mac, and Linux. PCM provides a large number of command line utilities for real-time monitoring. The basic processor monitoring utility is also called PCM, which is a tool that can measure all sorts of things, including the CPU and memory energy consumption.
The ARM Development Studio offers energy profiling possibilities for embedded devices with ARM chipsets. Capturing energy data is part of its streamlined performance analyzer. But capturing of energy data is deprecated now according to the official documentation, with no mention of a successor. And lastly, there is OClean, which is an energy profiling tool for JavaScript and TypeScript application. It creates detailed measurements of CPU time, CPU energy consumption, and RAM energy consumption for each component of the application. It is integrated into VS Code and can show the energy consumption directly in the source code, down to the exact line of code or library call. It can also be integrated into your tests. For this, Jest is currently supported.
There are more tools which are more specialized for certain programming languages or environments like cloud or Kubernetes. If you want to find a list on tools, you can go to the Green Software Foundation GitHub repository. Now we have talked a lot about the CO2 footprint of software. While greenhouse gas emissions are the main driver for climate change, there are also other environmental aspects in our modern digital world. We briefly look into the water usage of data centers and the environmental costs of hardware manufacturing. First, let's look at the issue of water usage. There are two ways in which data centers use water. The first one is indirectly by using power to operate their infrastructure. The production of power in plants consumes water. Fossil fuels and nuclear power plants convert water into steam using heat from their heat source, and then the steam rotates a turbine, which generates electricity. Water is lost in this process due to evaporation or discharge as effluent. Also, hydropower plants lose water due to evaporation from open tanks.
Direct water consumption of data centers is the result of cooling and humidifying. IT equipment produces heat during its operation. To prevent equipment failure, the temperature in data centers needs to be kept below room temperature. This is usually done by cooling the air using cold water, which results in water loss due to evaporation. Another direct water usage is humidifying the air in data centers because dry air increases the likelihood of electrostatic discharge, which can severely damage or destroy IT equipment. A study from Virginia Tech estimates that indirect water usage makes up 75% of data center water consumption in the US, while direct water usage only makes up 25%.
Large water consumption can lead to environmental problems because less than 1% of water on Earth is available for human consumption. In the US, data centers are among the top 10 water-consuming industries. There's an incentive to place them in regions where there are a lot of solar energy sources. but these are oftentimes regions where water is scarce, so-called water stress regions. A Nature study estimates that the percentage of drinking water in direct water usage of data centers in the US was 57% in 2019.
So, all major cloud providers have stated that they want to be water positive by the year 2030. This means that they want to return more water than they use directly. The main ways of doing that are increasing the efficiency of cooling systems, moving to a lower percentage of fresh water by using more recycled water, and funding water replenishment projects. Our personal contribution to reduce water consumption is the same as for reducing the carbon footprint. By writing greener software, we can contribute to lower the computational resources, which helps reducing direct and indirect water usage. On the other hand, we can also study the environmental reports of cloud providers and make a conscious decision on choosing a suitable data center where we run our code.
The result of increasing computational demand is also that more and more devices are produced and purchased. There are several environmental aspects associated with the production of IT equipment. Firstly, all processes in the chain of production, like mining the raw resources, the manufacturing process itself, and the transport of resources and the final equipment have a CO2 footprint. This can add up to about 1,750 kilograms CO2 for a single server. And secondly, mining for scarce resources has a direct environmental impact due to erosion, loss of biodiversity, and contamination.
Mitigating the environmental footprint of hardware manufacturing also has the same components as water usage mitigation. By writing green software, you minimize the usage of computational resources and help minimize the demand for new hardware. On the other hand, you should again search and study environmental reports of cloud providers. There they will mention their strategies for a circular economy, like recycling, reselling equipment on the secondary market, prolonging the lifetime of equipment, and waste management. Change cannot happen overnight, but there are small steps that we can do if we want our software products to be more environment friendly. So, we also want to share some strategies that you can implement to move to a greener product.
Green software by design. Keep green software practices in mind from the very beginning of a new product. You can start by educating yourself and your team about green software and bring the discussion directly when a new project starts. At this time, only a few decisions have been made, and it might be able to implement green software measures into your project. If a project is already in the world, it's way harder to make changes or justify the expense of transforming them.
Green requirements. How can requirements be green or greener? For example, by only requiring what the customer actually needs. Requirement management is a really complicated topic, and trying to figure out what the customer really wants is not easy. But it pays out, not just in saving of development time, but also further down the line. Code that has not been written does not need to be compiled, deployed, tested, or maintained, reducing the workload of every step. Also, there is a trend of adding AI to everything, even to remote controls or coffee machines. It's doubtful that this is really what the customer wants. New trendy technology should not be added to everything. Here we need to ask ourselves where this requirement comes from if it's not from the customer.
Rethink the accuracy of stored data. As said at the beginning, everyone and everything collects a lot of data nowadays. The amount of data only grows, which drives the amount of storing the data somewhere. We should rethink if we need all this data and also if we can reduce the accuracy of that data. We have an example for this problem in our company. Among other data, we store the wall thickness of pipelines for our pipeline inspection data. The wall thickness is stored in millimeters. The data type is float with a precision of 8 digits. We need to ask ourselves if this precision is really needed. What would it mean to store a millimeter value in a double? There's always the feeling that we need to be as accurate as possible in our calculations, but these numbers have no real value once you go into micrometer or nanometer precision.
So we always have to ask ourselves which precision is enough, which data type is the smallest that we can use to reduce the overall data. This matters as a single inspection in our company can have multiple terabytes of data. And you know, less data means less data to store, copy around, and read in for calculations. This question also applies to data that we store within and use within our programs.
There are data centers that run on renewable energy. This is a good start when you want to move to a greener product. As shown before, there are services like the Google Cloud service where you can look up which cloud region you want to choose when you want to reduce your carbon emissions. Also, more and more companies install their own solar panels to cover their energy demands partially or completely. This is an investment for sure, but it will help to move the overall power generation to renewable energy.
Clean up code. That can mean the removal of code that is not used anymore, which is a good idea for many reasons. Code that is unused still needs to be compiled, deployed, tested, and maintained somehow. This creates a lot of effort. Keeping code that is unused also contributes to code bloat. Code bloat can make the program less efficient and slower in the end. This can also happen when software engineering principles are not applied, like reusing functions instead of rewriting or copying them all over your code base. Another contributing factor is when principles are applied that are not necessary to solve your problem, like using object-oriented design when it's not needed, and a procedural approach would have been enough. This is something we have to keep a constant eye on as code grows faster than it can be cleaned up or refactored.
Clean up data. This means there needs to be a strategy to clean up data, preferably automatically. I think we all know the problem of test systems that write some data to the hard drive and the data needs to be kept there for a while to be able to check the results. But at some point, the data needs to be deleted. Otherwise, the hard drive will at some point at capacity. There has to be policies for this because cleaning up manually is a hassle and can be forgotten. It's so tempting to not want to deal with these kinds of issues and just buy a new storage system if the old one is full. But that's not sustainable, and the new data storage will also consume energy again. This is like the cleanup code issue. It has to be constantly worked on in order to not spiral out of control. To conclude.
Worldwide energy consumption is on the rise. This has many reasons, like the acceleration of AI services, especially in recent years. We saw that programming languages which are compiled directly to machine code are the most time efficient, and that correlates directly to CO2 emissions. While RAM plays a role, it's not nearly as big as the role of the CPU. But there are more things to consider when choosing a programming language, like if it's fit for your purpose. If this topic is important for you, you can use tools to measure the energy consumption of your program, and you can even include this into your testing routine. Water consumption and the need for new IT equipment also contribute to environmental damage.
We showed also how you can already take small steps in order to move to a greener product. While we cannot influence directly how sustainable the energy of our countries is produced, we can aim to do the small steps ourselves. This includes trying to reduce the CO2 footprint of our programs by using energy-efficient languages and libraries. This is our own contribution to a greener future. Thank you.
Thank you.
Questions?
So the deep broken language, does it do? Is it not also compiled to binary code, machine code?
Sorry, I didn't understand.
The deep broken language, does it count towards the C, C++, Rust parts of languages, or more to the Java?
Is it garbage collected?
I'm not sure. This is what I'm asking.
So the D language.
The D.
Yeah, as far as I know, it is garbage collected but compiled to machine code. So it's like a mixture, if you want. Yep.
I have a question about the algorithm you were showing.
Mm-hmm.
I don't think you have to materialize the Cartesian product because you can just do a partial sort copy.
Yeah, we could. We tried to keep it easy for us because we're not experts in all of the other languages. So we try to making an implementation that is comparable between the languages. So the solution will have the same approach for all of the programming languages.
But my other concern is you said when you were looking for an example, you were looking for something that wasn't just an algorithm in the standard library. And it essentially just boils down to a sort. And so I worry that the results that you have may be skewed towards
Yeah, to be fair, this is not a scientific paper. We did not look into any like super complex calculations that they used in their paper. We just used what we're familiar with and what we're comfortable implementing in different languages. But you might be right. It might be a little bit unfair to the other languages. But then again, all of the languages have to implement some kind of sort, and they also need to be fast in their language. So I guess it's still comparable.
Yeah. And another motivation for choosing this algorithm is that this is something which you could be confronted with at your job. Yeah? It's like a business software algorithm. You could be tasked, could work at a company where you need to implement this. So this is something you could like come across, and we wanted to see how it feels like in different languages. More questions, please? Yeah, there.
If you want to optimize the code further, you create a purpose or something?
Sorry, I have to come over there.
Yeah, I just looked at your code and I saw that you cloned the string, I think 500,000 times in C++ and Rust, but in the C implementation you just copy a char pointer. And that thing have a big impact. And also the C++, no, the Rust version, you run it through cargo run and release, but the C and C++, you run the binary directly. And I think the cargo has some overhead.
Mm-hmm. Yeah, so there's basically two questions. I will repeat them now. The first question is like, does it make a difference if the string gets copied around, which happens in the C++ in the Rust implementation and not in the C one? Yeah, this could make a difference, but if you look at the table, the difference between C++ and C was so small that it cannot be that big difference. And the second question was a Rust question, because Rust is run with cargo run, and the other applications are like the C++ ones are run directly by calling the executable, and if this has an overhead.
Yeah, you can run the executable directly.
Yeah, Yeah, and an additional comment, you could run this Rust executable also directly. And yeah, there could be a very small overhead from using cargo, which needs to figure out if the executable is already there and then run it. Could make a small difference. Again?
So optimizing compilers typically have a mode to optimize for speed and to optimize for binary size. Is it worth having a mode to optimize for energy efficiency, or is that just going to end up being the same as the optimizing for speed?
As we saw in our experiment and also in the paper, run plays a very small role, and the biggest role is the CPU. We didn't test any GPU stuff, so I cannot answer that. But I would say that optimizing for speed is also optimizing for carbon emissions or lowering carbon emissions.
Do you see any interpreted languages and things that are usually or have been chosen at least in recent years for the convenience of writing something quickly? And it's like an economic incentive to produce something, right? Do you see any tendencies in the world in the form of initiatives or market dynamics that would push people just organically to make the choice of creating something faster and more efficient?
Yeah. So I think there is a trade-off. Yeah? All languages exist for a reason. Yeah? There's a reason why C# and Java exist. And if you really care for performance of a certain part or energy efficiency of a certain part, and you measure it and optimize it, but you want to use C# or Java because you have the people available to do that, then one good choice is look for an optimized library for that purpose, I guess. And this is a valid strategy, I guess.
But also there is some incentive from the outside, because at least for the EU, there's a new law, it's called a law or thing, where companies need to report on their carbon efficiency, and this includes all companies, also IT companies. So I think in this year, they increased the number of companies that have to report in this report, and in the next years, they will include like all of the companies. So at least in the EU, there is an incentive to lower your carbon emissions just by reporting this to the EU. Thank you.
Yeah, thank you.